Okay, question 7. It looks like a nasty question with that, but it's actually a lot easier than it looks. So figure 10 shows a small steel ball held at height h. It's released. This height is 1.4 meters. Calculate the time for the ball to reach the ground. You use the equation and it tells you that g is 10. So we know that height is 2 lots of 1.4, so that's 2.8. We know g is 10, but the crucial part is we want to calculate time t, and this is t squared. So no, the opposite of squaring is square rooting, so therefore we're then left with the equation that we need, which is t equals the square root of 2h over g, and then we just plug in the values. So t equals the square root of 2h over g. 2 lots of 1.4 is 2.8, divided by 10. That's going to come to 0.28, square root it, and we get 0.529, or 0.53 seconds. So it looks tricky, but really it's just showing, do you know that the opposite of squaring is square rooting to get t? Next one, 2 students use the arrangement shown in figure 10. They use a stopwatch to time the ball. The students repeat the measurements many times, but their average value is very different from the calculated value. Why? Well, the crucial part is they're using a stopwatch, and therefore we're going to have human reaction times. So there's lots and lots of error in that, systematic error in the way that they've set up the practical. So the percentage systematic error is high due to human reaction times. Suggest one improvement they could make. Let's change that to light gates. We know that that works. So use light gates in a data logger. This will remove human reaction times and therefore reduce the percentage error. The other one in the mark scheme is it says you could use a stroboscope or drop from a higher height. So a stroboscope is just a flashing light, and what will happen is it'll make it easier for you to see the drop. But by far and away the easier answer is light gates and a data logger to remove human reaction times, because that fits with lots and lots and lots of previous questions. Okay, next one. A box is falling towards a hard floor. Bump. The box hits the floor and crumples a little, so we've got a bit of a crumple zone there. Lovely. The momentum of the box, so delta P, is 8.7 kilogram meters per second. We're happy with those units. It comes to a rest after 0.35 seconds. So we're going to need frogs, puke, tarantulas. In your mark booklet, it'll have F equals mv minus mu over t. They're the same one, but it's what's our change of momentum. Well, our change of momentum is this value. So we want to find out the force, so that's the momentum divided by the time. So F equals delta P over T, 8.7 over 0.35 equals 24.9 newtons, or 25 newtons. The next one, we've got the ball is held in a clamp. This time we've got 3.8 meters, but we don't need to change that. The ball is released and it falls. At S, the momentum is 0.4 kilograms per meters per second. It says calculate the mass of the ball and the acceleration equals 10. So we're just going to have to use the same equation. So we've got, we're going to need our magic puking vampires, and we want to work out the mass. Now, the crucial part is we need to work out the velocity first. So this is a really tricky question. It's a beautiful question though. So if I just write that equation up here, well, we know that we're going to need magic puking vampire. But for us to work out the velocity, because we know the momentum, but we don't know the velocity. So it's then a choice of, well, what can we use? Well, we know that we can work out velocity using, so A equals V minus U over T, or V squared minus U squared equals 2AX. So now we're just going to check, have we got a time or have we got a distance? And it tells us we've got a distance. So get rid of that one. So the next part now is we want to work out V squared, or V. So we now know, well, that's the U squared's got to go to that side. So V squared equals 2AX plus U squared. We don't want it squared, we want V. and then we just plug our values in, and then that will tell us velocity. So the crucial part is we've got to rearrange this equation first. That will then give us the velocity, and then we plug that into this over here. So here's it now modelled neatly. It's a beautiful question and a tricky one, and we're after a value of 0.046, and we can see I've left that in there. So we need the final velocity using v squared minus u squared equals 2ax. Rearrange v equals the square root of 2ax plus u squared. Well, it tells us that at this position it's 0, so it's 2 there, times the acceleration due to gravity, 10, goes there, times the distance x, 3.8, so we've done both of those now, plus, and it started at 0. So that's going to give us the square root of 76. We've now got the velocity is 8.72. So it's taken us a lot of work to get that. And now we can plug that into mass equals the change in momentum divided by the velocity. It told us that the momentum is 0.4. That's here now. Divided by the velocity that we worked out equals 0.046 kilograms. So really, really tricky question. But what we're pulling out here is this is a multi-step equation where we're rearranging v squared minus u squared equals 2ax to tell us v, and then that's being plugged into momentum delta p equals mv in its rearrangement. Okay, lovely question, but a tricky one.